by different people, and that might be the base of the SDV. We'll show you what this means after. And then before to conclude, I'll show you some study I found a couple of months ago, which is L4, which is a microkernel verified and approved. So, what's our goal? Either in this presentation and more generally in my PhD study, being able to verify property, improve quality of the Linux kernel. Linux kernel, not only, as a Riva, we would like to import any software within distribution, and we think any distribution, not only Riva, is the specific corner of the distribution process of software between people that are contributing and making software and people that are using them. We are making the link between both, and thus it seems important to us that we are able to bring the gap between both on the quality issue, not only with body force and not only with backported patch, but also with the verification we can add on our side. Why we were interested in the kernel? Because it has a lot of patch, and even if, as I showed this morning, from a number point of view, there's not such differences. We plan to check on the semantic of the patches we have between vanilla kernel and distribution kernel to check whether it has a real influence. And in this context, it has a lot of sense to be able to check quality along what we distribute. So as I said, it's the differences are not that much important, as I presented this morning. However, we can state that we have specific patches for the distribution, which are integration patches. Maybe not for the kernel, but for any other software. We have backports for fixes, for upstream features that are not yet available in the version we are using. And some part of the kernel might be less tested than the vanilla ones, and less tested in different contexts. So they might expose different bugs. I made a small backlog of topics in the paper I will present. So you can see that the main topic is Linux, and the second main is then you have interface, and then logic. So this gives you a good insight of the results of my study for now. Many of the papers I found were around using model checking to verify the usage of interface in drivers, and Linux is because I was searching for Linux things. There are other keywords like VM programs, which are more linked to Microsoft. Slam is the same. We present them after. And Cigar also. You have this modeling environment thing, which is more linked to the model checking aspect. And a small keyword, I don't know if people in the back can see it well, but you are looking which have popped out, because maybe there are talks about verification of block in the code. Because I think it's obvious for anyone here, but for example, taking a spin lock twice is not that good. So checking locks is very important. That explains why we have it. working out. So, from standpoint probability, this will present the work that has been done by Stanford people around verification that led to the foundation of probability at a certain company, which I suppose everyone here has heard about. They are kind of contract with the Department of Homeland Security to check many open source software, and I will present you what they are doing inside the tool. So there is the main part is metal, and there are another paper that I found very interesting. They give some backtrack and feedback from their experience on both static analysis and model checking. So from the point of view of my study, since we are more interested in the model checking aspect, it was very interesting to read this. So meta-level compilation, it's not complex to understand. It's just the process of manipulating program compilation. So basically, in the paper, all they did was to fork the GCC at the time. They added from the inside to have some kind of plugin mechanism that allows them to write language, which is a method that I will present just after, and that allows them to check for what they call interface usage during the compilation phase. And the goal is to have the programmer writing checking rules for systems. So systems does not stand only for code, but for anything that goes through compiler. They run it on Linux at the time. It's a paper from, I think, 2001. And so they run it on Linux, they run it on OpenBSD, they run it on an embedded system which is called Flash. And I think it's all related. Why not model checking? I am this slide because it's an important part of the paper, which is paper number 1. And they explain why they did not at the time choose model checking to implement the mechanism. And because in the mind it was costly to do model checking, it's not easy to write a model checking mechanism. Model checking might not be exactly right because people that are writing it does not have a complete view of the whole system. They might miss something. They are oversimplifying sometimes, and in fact you end with something that is in theory to their point of view a good system, but applied to the correct types, it does not give so good results. It's their point of view in this paper, at least. So they introduced the meta language, which is a qualified static analysis method, and it's a higher level state machine-based language running inside the version of G++, which we call it G++. It is used to find bugs and also hotspots. So hotspots is simply for optimization purpose to find where the code spends most of the time. And being state machine based, you have some. I don't have any example of I didn't put any example of the code itself, but basically you explain, you describe describe the features you are interested in the code you are parsing, and not exactly parsing, but in the code you are manipulating. And then you describe the state machine, so the event and the transition you want to do on on this part of the code. So it's not free software. And so that's after a couple of years working for free software. Some guy started a project which is called Smash, which is still being maintained, and which tries to implement what has been done in this tool, but not as a G++ plugin. I think it's because at that time there was no plugin. As far as I remember, it has been created in 2004, and GCC plugin are just 1 year old. But so he handled also the parsing, abstract syntax to itself. Maybe it would be most right to convert it to GCC plugin. Don't know. And in another paper that they did in 2004, the same people gave their feedback on static analysis versus model checking. So they have spent several years working on the tool. I'm not sure at the time the company was founded, but they had enough feedback to give an advice, and they gave it. So the methodology was to use the meta-level compilation tool, which we qualify as an hands-on method without any model of the heap, and trying to avoid annotation in the code. And they compared it to model checking using classical model checkers. I don't remember if they gave the correct name. And they took two approaches for the model checking part. One was they automatically extracted from source code the functionalities to check, and the other they directly model check the code. So this second approach is interesting for my use case, and thus that's why the paper is really interesting on this aspect. And the results are quite strange for the first time. They state that model checking did not find more bugs as we had expected. They expected model checking to give more bugs from static analysis. In fact, it gave 4 times less on the flash embedded system. I don't remember the figures for the other case, but it was not that important, but it was also less than their static analysis technique. They also say something that is very interesting for us. It's that it's easy to find bugs as soon as the code base is very large. So it means that anyone who wants to help improve a large project, being either the Linux Kernel or something like Firefox or LibreOffice, you just have to do it. You will surely find bugs. They state an important thing to me, which is that it's easier to write how a property should be checked than all the case where it can be very clear operating. So this might have an impact on the future work that I will have to do. And they also state you have to avoid being too general. By this I mean it's not useful to try to create one super master rule that checks everything. It's better to do simple, limited, and easy to qualify and understand rules that check one thing. You can see the same as the so-called Linux philosophy. Some errors have been dropped. So this point might be disturbing, but they state that sometimes when an error is too complex either to understand or to fix, maybe it's not useful to want user input. By user, they target anyone. so I'm not sure it's really valid for any user. Let's say a kernel maintainer that tries to fix as much as possible issues. I don't think this Linux kernel can be useful. But I think this point is more from their commercial experience, and I'm not sure it's very important for us. But it's interesting to know that from the point of view, some error might be what it's not useful to warn about that. And another point is that not all bugs matter the same way. You have to order bugs themselves so that the user can decide what is more important and fix priority to fix. Define priorities, the bug to fix as soon as possible. Another point is that model checking is in practice less powerful to the point of view because it needs a good environment model, and the state it is inefficient on large projects. So keeping that in mind, because Microsoft has another point of view. In the first paper, which is dated just 1 year before the millennium, they explained that they had a meeting aiming at improving software quality in the department dedicated to software quality. And they wanted to check interface usage, just as people from Stanford. Maybe it's in contrary for the difference, because the Stanford people published after. And they put focus on drivers. I think it's obvious why. Because at the time, Windows was not very popular for its stability, even if it's not yet the case. So after this meeting, 3 research projects were launched. SLAM, Volt, and PSP. SLAM is a model checking tool that I will present after. The 2 others are kind of failed, not totally. Volt was a new programming language with ability to set up pre- and post-condition types that will allow to check the correct usage of the interface and any variables. Now it has finished as a Visual Studio plugin which does some checking on the .NET code. So it was not that failure. And ESP was the same as SLAM, but with a different trade-off. And I haven't been able to find any other references to it, other than the mention of the creation in this technical report. So I suppose it's dead, but it's still software, so you can't really. So now SLAM. In those 2 papers or 2 main contributions, a model and its model checking algorithm. So the model is a Boolean program, and it's pretty easy to understand. You just have to take you keep the control program, you remove, well, you keep all variables, but you change them to Boolean variables. And it gives you a Boolean program which has 2 interesting properties, in that reachability of the label and combination are decidable in this context. So we can do some checking. So for the checking part, we introduce the Boolean program reachability problem, which is based on another well-known problems that I don't remember the acronym. The idea is basically whether we can reach a level in a tree, and the model checking algorithm is based on the results for the TFL results. So since it aims at checking interface, they also have to provide a way to describe interface. So they contributed a language for this, which is called specfic. And it's once again state machine. I was to describe interface with and has some interesting properties such as being able to enter subtract or things like that. Again, it's lots of code, so it's not that easy to find precise information. But and we'll see that after I tell you about. And they also proposed a way to plug everything together, which is called the single process. It's basically pretty easy to understand. It's an abstraction refinement loop. So you have the C2BP program that converts C code Boolean programs. Then a model checking tool is applied to check whether it holds or not. And you have some kind of backtrack that is done to check that if there is infeasibility or feasibility that is found by the model checking system, that should not be there. And Newton program checks that what you have found in the Boolean program stands also in the C program. Because as they show in previous paper, you might find things in the Boolean programs that are not true in the C program. So this way they can only check what is interesting to check in the C program and it allows to, because something that one not that bad. And after 2 to 3 years, the SLAM project became powerful enough. At that time, there was still quite a lot of false positives, something like 15 to 20%. They also had timeout issues because of searching for reachability in the Boolean program. So they are timeout, and sometimes it was it. So that became the basis of what is called SDV, Static Driver Verifier. And at the time they had a meeting with all the core managers so that it could be integrated in the workflow of the company and not being just a research project. So it began to be used by the driver team, which had contributed most of the checking rules. Only 60 were written by SLAM software. So it's interesting. It shows that driver maker are a good source of rules to check. They are the one which are the best position for this anyway. And one interesting fact that is exposed in the paper is that using SLAM and SDV, when preparing the driver model for the so-to-come next version of Microsoft Windows, which is now Windows 7, they noticed that some rules were too complex to check. And instead of trying to make a complex rule or modifying SLAM software, they took another approach. They simplified the API so that it was easy to check. And that is, I think, a very important point. They did not adapt the checking tool to the API. They redesigned API so that it can be easily checked. And the latest version, according to them, brings less false positive, timeout, etc. Since we don't have the code, we can't test. And now, start should be more interesting for you. Here, the Linux SDV. So there were a couple of people working on this, which are from project. And let's start with that one. It has nothing to do with the plan. It just starts solving. So I think anyone else understand what is SAT swapping. It's just a framework to detect errors in large code base. So the large code base part was very important to us and to them. And follow the advantage claim. I do not have time to check really with the framework. It's free software now. So we can use it, we can test it, we can patch it. Its precision, because no abstraction is done, contrary to the C to Boolean abstraction. But now the deal is direct level. They convert code into Boolean formulas so that they can apply SAT solving techniques. And two things interesting by doing this is flexibility and complexity. It's flexible because you can do it with any language. Playing it is on C++, could be Java, anything. So it means that it should have no impact that the Linux kernel has some part of assembler code. You could be able to use it too. And capacity, because both for intra-procedural and inter-procedural, they can use forms of the Boolean formulas that are adapted and that allows to speed up the process more. This is more interesting for the inter-procedural part because they just have to compute a summary of the function, which you can see it as a SHA-1 fingerprint, and it allows to more efficiently check inter-procedural analysis during inter-procedural analysis. So once again, we were interested in what they called temporal safety properties, and they gave an example with checking logs. What to understand by temporal safety properties, it's just the correct interface usage, once again. So for now, everyone has just been interested in checking the usage of interface. They checked for memory leaks in a couple of projects, and as far as I remember, they found a couple. I don't remember exactly how they did the checking of the memory leaks. Another paper, which for two, which is called DD-Verify, aimed at model checking SHA memory program. They were interested in this because, as you know, SHA memory program have bugs that might be very complex to expose and to understand and to travel. So if we can get a bit of those or other formal techniques, it's always a good thing. They also contribute a concurrent model, so a model for the, let's say, threaded parts of the kernel API. And the implementation is DD-Verify. It's free software, but it's quite full paper as far as I remember. It was around 2003 or 4. And it's kind of hard to find any traces of source code for now. So they do concurrent software verification with predicate abstraction. Predicate abstraction is quite usual. Their contribution in the concurrent software part. They process the source code to an annotated version. And they simulate concurrency with spread. So this is the verification of the model checker that I used after, because if you want to keep control of the machine, you have to use the static and built-in number of threads. And not all model checker are very at ease with shreds. There are model checker with infinite thread support, but there was also a problem with them. And they also use the cigar-like loop, so abstraction financing. So they check and they improve it. There are two main results that model checker performance are critical. It's where most of the time is spent. And model checker in concurrent context is very bad at that time. Now we will talk about Kernel once again, for those who were here this morning. So it has been introduced to London what they call collateral resolution. And as far as I remember, it has been presented already in the Linux symposium, so maybe some of you already know a lot about it. For example, that motivated the work was the removal of the check region function. So prototype change of some function and the introduction of new way to pass argument between the space and kernel space. And the common point between those three is that it took years to complete the full process. Some started on 2.4 and finished on 2.6. It's huge work, and sometimes it's lazy because it's done by people introduce this sport. So they felt it was necessary to add automation to it, and they introduced Kernel with the semantic patch approach. So semantic patch is quite easy to understand. It's just that you take a patch, you remove the line references, and you add the cells to it. So basically, instead of having the context specified by lines, it's specified by units of variables or singletons. This patch format was chosen because it was easy to understand for kernel developers and also self-explanatory. So it was a good way to exchange information. It was textual, so it's easy to read it. No need for special software to read it. And it can serve as a whole documentation of changes. They have to comply with the identification of the zone of the code to modify, the description of the new code, and the impact to the text. So, in fact, you can see that the source code that is being analyzed becomes a model. And they explain that the way semantic patch is implemented in the tool is just a plain CTL formula. And CTL formula is just model checking technique. So in fact, Kernel might be seen as a model checking technique. There are also some more kernel developer-oriented information that are available in a couple of papers. And I think this is one presented here. And because it is model checking based, then they use it to verify. Instead of having a semantic patch describing the evolution, they extended the semantic patch semantic to add some verification capabilities, and it allows them to check for allocation, deallocation, values of memory of the free, the classical new pointer reference, and also in papers they use to find automatic labels and automatically work around them. So it's very interesting. There was been some work by a student a couple of years ago that has applied Kernel verification to several open source projects. As far as the it was focused mainly on OpenBSD, and it discovered a couple of bugs that have been fixed while it discovered them, because did not work on the development version, but on the startup version. So he found bugs that have just been fixed, but it showed that we can use proximal tool not only for kernel verification, but for any software verification. And this is also very interesting from our point of view. Another tool is Life. In fact, it's also a framework that makes use of annotator, so that I told about this morning. So for those who are here this morning, it's quite obvious. For the ones, you have kconfig, which is a variability of configuration, and this creates a model which they call variability model, and this model has some kind of correspondence in the source code, which is called the variability implementation. Basically, just a bunch of if-def in the source code that are making use of the defines of the kconfig. And the goal of Life and Undertaker is simply to check that both are consistent, so that any configuration option has code that use it, and vice versa, that you have code that is enabled or disabled by verification. They found a couple of bugs, and it's quite interesting to use. It's pretty new. It has been released this year or last year, and we can now state in question SDV for Linux. Because someone in Telegram wanted to port SDV to Linux. Since SDV has been done in a closed source manner, he has no access to SPIC, he has no access to the model checker being written by Microsoft. And they have to contribute a model for the Linux driver lifecycle. So basically, module unit and module unit. And they contributed a check of the RPO API. It's pretty interesting, but once again, it looks like a one shot and nothing really works for a long time. And now, some fun things so a couple of months ago. It's L4 kernel, micro kernel. In fact, it's very, very compact because it's a micro kernel. But I found it interesting because it's a mix of C code and assembly. That's the Linux kernel. Not only they contributed the proof with automated tool and computer-assisted tool like Isabel. They also contributed some rapid development tools for kernel, and more especially for micro kernel. They made some prototyping using Haskell to prototype before implementing in C. So in fact, they had the source code, they had the code verified before it has been used. This paper, which is from, I think, 2010, states, however, that they did not have completely finished the verification of C code, of the current implementation in C code, but on the previous implementation, it was finished. And two major facts. The verification has no performance impact. So, doing, another way to say it is that doing closed code doesn't imply doing slow code. They managed to have a fast microkernel, which is good. So this is interesting. And however, they use the triple version of C99 with the main thing of Forbidden. I don't remember exactly which, but it was like you can choose address operator, so quite important limitation from our point of view. So conclusion is that what might look like not so new area, in fact, has got some work, but it seems very uncertain. So several works that have been started one shot and not being continued after. The only really work is we are following, it seems to be Kernel, and so it's a bit sad. So the next step for myself is that what we would like to achieve is to check code at the compile time using GCCNet. GCCNet, probably you don't know, but it's in fact it's like Metal. It's some Lisp-like language to manipulate the GCC input. It's being done by someone from French CERA, Alexandre. And we have now a student which is working as a Google Summer of Code with Net for creating networks that could allow to check the interface usage of any software. So if you're interested, we can talk about this after. And another point that I would like to do next is a more formal verification of some part of the kernel, and maybe atomic operation, because I saw many events around things that have been fixed in the project for the previous year. And I did not saw many work to check this part. It seems to be an important part being used by several other parts of the kernel. And for those who were at my presentation this morning, it lies in the ARC subdirectory, which is the one which has, for now, the most bugs if we can present bugs. So if you have any idea or any point that come to me where I should focus, I'm open to any suggestion. And this is the end of my talk. You have many references. Those interested can ask me, I could give them the slides. And if you want to, not my mail. Any question? I know it's the last one before the keynote. Everyone is.
You had to recommend one tool, which one would it be?
It's quite difficult since I did not really have time to use solidly any of those. I started playing around with Taker a couple of weeks ago. It seems great, but it's limiting to configurability. I think Kernel is one of the most promising. And I think combining the Kernel aspect with the GCCNet aspect would be very interesting, because this way we could leverage all of the GCC parts. Could be more easily integrated with the production toolchain, etc. No more questions?
More or less.